All right, so today what I want to do is kind of prepare you to do the next lab. It's going to take me 2 weeks to discuss the material because I'm using the time in class. Just 1 second. I'm using the time in class or in lab to talk about chapter 27. That way we can talk about measuring circuits. A lot of the labs we're doing this semester will involve us building circuits and making measurements because those are the easiest kind of lab we can do when the course is online. The other labs require expensive equipment. So I know I'm covering the lab a little bit out of order, but with the course, but that's because most of the labs involve circuits. So I do expect you to read maybe half of chapter 27 this week and maybe the other half next week. So this week I'm going to give you kind of a basic description of some of the fundamentals of circuits, and then next week I'm going to do a more general description and then actually talk about how to do the measurements. Apparently I didn't have enough time in the first class to actually talk about you doing the measurements. So what I'll do is wait till next week to show you how to use the multimeter. Okay. The other thing, just as a reminder, your properties of charge, the actual lab is due on the 25th. So if you ever have questions on that, let me know. So my goal today is really to discuss how we get electrons to move through a conductor, and for us it's going to be a wire, and how to make measurements that characterize the behavior of the electrons in the conductor. Okay, because that's what we're going to be doing a lot of that in this course, and some of you folks are going to take Engineering 17, and that's all you're going to be doing in that class. But before I get started, do you have any questions regarding the properties of the charge lab? Okay, so we will move on then. So let me begin by, just 1 second. Let me begin by, Jacob, let me take a look. Your question. Is there a particular ground that works best? You're talking about for the properties of the charge lab? I mean, you can use any pipe, any metal pipe. Because they all go, metal pipes will go into the ground, so any metal pipe would be fine. I mean, there's other ways to do it, but I think that's the safest way to do things. Yeah, if the pipe is coated, then that's going to cause a problem. If your faucet is metal, right? If the faucet in your kitchen or the bathroom is metal, then that'll be fine.
Did he also make sure that the electroscope worked? Like it could also be the coating on the hanger itself.
That's right. Yeah, and I think I mentioned 2 weeks ago that if you use like something from a coat hanger, because I use a coat hanger, I sanded it down. Okay, worked fine with the PVC. So you're concerned about the electrophorus?
I noticed that when I was doing it, I had to charge mine a lot more than what I'd have to do with PVC.
You do have to charge it quite a bit. I mean, you have to rub it vigorously, either with the fur or wool. So Jacob, what is your plate made out of? It's a paper plate? Okay, it should work because my paper plate worked great. What I discovered over the weekend, because I had one person said the cardboard didn't work, and then I was surprised. Then I had another person tell me the cardboard didn't work. So I tried it, and the cardboard didn't work, which I guess it means it's not a good insulator. I use corrugated cardboard. I would have thought that that's a great insulator, but the paper should work fine. What are you charging with? Are you using styrofoam? I use a styrofoam cooler. I mean, you guys saw me. Saran wrap should work too. I mean, I have a video of one student, he used saran wrap and it worked fine. You can use a transparency.
I tried saran wrap and it just it wasn't working, so I just used a cooler.
Yeah, and the cooler worked fine for me. The problem with the saran wrap is it gets it's not stiff, right? But last semester I did it with saran wrap and it worked. I think the cooler works better, or just a styrofoam plate. And some students they had a big piece of styrofoam and they just, it's fun to listen to those videos when you guys are rubbing the styrofoam. It makes a nice sound. Oh, you couldn't get the saran wrap to work? Okay. No, but you're right. The styrofoam works the best. Okay, so yeah, try the cooler. I mean, it doesn't have to be a cooler. I mean, if you have a styrofoam plate, that's fine too. Okay. So yeah, try the cooler. I mean, it'll work fine. And you be careful, don't press too hard on the cooler. You want to use the flat side of you want to make sure there's a nice, smooth, flat side on the cooler you want to use. Okay? All right. Let me know if it works. Should work. Okay. So what we want to look at is how do we get, okay, thanks, Jacob. How do we get electrons to move through a conductor? And the reason why it's important, because the lighting in your room, for example, I mean, that's requires to get electrons to move through a conductor. And we're going to focus on electrons in a wire, okay? What I'm going to talk about can be applied more generally, but our focus is on getting electrons moving through a wire. So what do we have to do? So let me draw a wire. Just any old wire. And this is a conductor, because if you have an insulator, it ain't going to work. And really what we need is an electric field. On Tuesday, when we finished class, or at the end of class, we wrote down this equation. That if you put a charge in an electric field, it's going to experience an acceleration given by Q E over M. And you produce, you set up a uniform electric field, your acceleration's uniform. It's the same value everywhere. Okay. Of course, I'm assuming the electrons aren't bumping into anything when I say that, but that's not true. Okay. So all I need is an electric field inside the wire. So I have to connect the two ends of the wire to something to make the electrons flow. So I need something to produce an electric field inside the wire. And a device that does that is a battery. Or a power supply. I'm going to focus on the battery. So, by the way, I'm going to talk about the battery. I'm really going to talk about the physics of the battery. I'm not going to talk about the chemistry of the battery. There's a lot of interesting chemistry that's going on with a battery, especially nowadays when you see electric cars, etc. But I'm not going to get into the chemistry of it. I'm just going to talk about the physics of it. And I guess if you took chemical engineering class, or maybe in your chem class, you can talk about, how the battery works. I just don't have time to get into that here. So what does a battery do? A battery gives the electron potential energy so that it can move through the wire. It's the same thing as if I took a marker, let's say I'm holding the marker in my hand, and I do work on the marker to lift it from my hand to some higher position. I've done work on it, and I stored energy in it. And then when I let it go, the gravitational field does work on it. The decrease in potential energy becomes an increase in kinetic energy of the marker. Same thing with the electron. The battery does work on it. The work done by the battery is basically increases its potential energy. Okay. And then the work done by the field on the electrons give it its kinetic energy. The work done by the field is minus delta U. That's what the battery does. Or a power supply. That's what they do. They do work on the charges, giving them potential energy, in the same way as when I do work in lifting up this marker from my hand to some higher position. Okay, so the work that I do is equivalent to what the work that the battery does. I give the marker potential energy, the battery gives the electrons potential energy, and then the field, the gravitational field, does work when I let go of the marker. The electric field does work on the electrons, giving them kinetic energy because the potential energy decreases. Are we okay so far? So the battery gives the electrons potential energy, and then the electrical potential energy is converted into kinetic energy. But we don't describe the battery in terms of the electrical potential energy, because it depends on how much charge you're moving. It depends on whether you're moving positive charge or negative charge. I mean, with a battery, you're moving negative charge, but if you're in an accelerator can move, a power supply can move positive charge in an accelerator. And so what we define is something called the electrical potential energy per unit charge, which is delta U over Q. We define the electrical potential energy per unit charge, and delta U over Q, which is also the work done by the battery per unit charge. This is called delta V. It's called the electrical potential, and I'm running out of space, difference, and I ran out of space here. Okay, so let me rewrite this. I ran out of space. Potential difference. Okay, so this is also known as the voltage. We also talk about it as the PD, potential difference. So the units are joules per coulomb or the volt. So basically what you need in a wire, you have to set up an electric field. The electric field is set up because of the delta V. Okay? The electric field exists because you have a delta V. You have a gradient across the wire. You have a potential gradient across the wire. An analogy to that is, you think about what gets air to flow. What produces the wind? It's a pressure gradient. If you have a change in pressure between my two hands, air is going to flow between my two hands. So if on this hand I have a higher pressure, on this hand I have a lower pressure, air is going to flow from the higher pressure to the lower pressure. That's analogous to our delta V. The delta V is going to set up a gradient. It's going to set up an electric field that's going to allow the electrons to move through the wire. Are we okay with that so far? Questions? So a battery is really a device that maintains a potential difference between its two terminals. That's how we'll describe the battery, or a power supply. Okay, I'm going to say the word battery a lot at the beginning, but it's just a device that maintains a potential difference between its two terminals. And when I connect a wire across the two terminals, then I'm going to have an electric field inside the wire that will cause the electrons to move. Questions so far? Just want to make sure that you have this down. Okay. So we've defined then the potential difference. This is one of the characteristics that's going to affect the behavior of the electrons in a wire. And really what we're really measuring global behaviors, right? We're not looking at the individual electrons in the wire. We're looking at collectively what's happening. I mean, that's kind of what you do in physics 215 when you talk about thermodynamics. You look at things collectively because we can't look at what happens at each one of the electrons. So one is delta V. The other one is the amount of charge or the amount of charge per unit of time that's flowing through the wire at any particular point in the wire. So one of the things that we use to characterize what's happening in a circuit is your electrical potential difference, also known as the voltage, or the PD. By the way, we're going to go when we get to chapter 25, we're going to say some of this. Anyway, the other thing is current. So let me define current. It's the amount of charge per unit time flowing through any point in a circuit. And we use the letter I to define the electric current, or to denote the electric current. If you want to know the instantaneous value, we take the limit as delta t goes to 0 of delta q over delta t. Of course, this is known as dq dt. If I is constant, if I is independent of time, then we can say all right, for steady currents. But if the current's not steady, then you got to write it as dq dt. Now we're going to be working with DC power. We're going to be working with batteries, DC power supplies, and we're going to be dealing with steady state currents. But once we start talking about other elements in the circuit and other types of power supplies, then this derivative is not going to be 0. I'm sorry. This is. Let me rephrase that. This is not going to be constant. It's going to change. Okay. Now, what are the units for this thing? Well, it's coulombs, right, per second, which is the amp, named after ampere. And the amp is actually kind of a large unit of current. So we tend to use milliamps. 10 to minus 3 amps is 1 milliamp. Or microamps. If you're talking about what's flowing through the refrigerator, it's going to be in amps. When you talk about what's flowing through different parts of your computer, maybe your power supply will be in amps, but then everything else will probably be in milliamps or microamps. Well, I shouldn't say everything else. Most everything else will be in milliamps or microamps. Okay, but your power supply will probably be in amps. Or maybe the fan that's connected to your power supply. Okay, so far, so we've talked about current, and we talked about voltage, which are things that characterize what's happening inside your conductor. Really, the third item that we want to look at, we will get to, is a quantity that's related to the property of the conductor, which represents an opposition to a flow of charge in your conductor. In other words, the more the opposition to a flow of charge, then the lower the current. That's the last item we need, at least for now. We'll introduce other items later on. Okay, but this will get us pretty far. So some examples of electric current are electrons flowing through a wire, a beam of positive or negatively charged particles from an accelerator, or in a plasma. Although in a plasma you probably wouldn't have a beam, but or an electrical solution, electrolytic solution that you would deal with in chemistry, for example. And I know some of you guys in chemistry, you guys do experiments in electrochemistry, right? And you talk about current in your solution. And there's some interesting calculations you can do based on your measurement of the current in your solution. So those are some examples of electric current. Now again, we're going to focus on electrons flowing in the wire, but our discussion is not limited to just that. I should really note for you folks that the current due to a positive charge moving to the left is no different than a current that's due to a negative charge moving to the right. They're equivalent. And the reason, and I should say they're electrically equivalent, because, you know, imagine you have an atom. Whether I add an extra charge to it or remove a negative charge, electrically, that's the same effect. Normally, I would show you a video demonstrating this, but because my computer is using too many sources, number one, the video doesn't work, and number two, I'm recording this for YouTube and I can't show the video. So I'm going to skip the video. I want to talk a little bit about the battery. And I really want to talk about the concept of electric current. So let me draw a picture, and I'm going to erase this. So let me draw my battery. This is the positive terminal, that's the negative terminal. And I'm going to draw a circuit. I want to draw a better circuit than what you see in the PowerPoint slide, because the PowerPoint slide essentially shows you a direct short. I'm going to put a light bulb in my circuit so that it's a little bit more realistic. So I'm going to take a wire, connect it to a light bulb, and then the other end of the light bulb is going to go to the other side of the battery. So many years ago, when people studied the motion of electrons in the conductor, they thought it was positive charge going this way that produced the electric current. They felt that it was positive charge moving clockwise here that went to the negative charge that produced the current. And we call that conventional current flow. Let me just call it conventional flow. I'm going to say something about the terminology in a second. Let's call this conventional flow. Years later, an experiment was done which showed that it's not positive charges that are moving in your conductor, it's negative charges that are moving. So in reality, it's negative charges going this way. So the negative terminal loses electrons and the electrons go to the positive terminal. That's really what's happening. We call that electron flow. But because a negative charge moving to the left is the same as a positive charge moving to the right, then it doesn't matter whether we use conventional flow or electron flow to analyze a circuit. It doesn't matter. You can use either convention to analyze a circuit, because when you do the calculations, you'll get the same thing. Okay? Now I want to say a word about this terminology, current flow. Your textbook makes a point of this. Now what's current? Current is charge flowing. So current represents charge flow. So what does current flow represent? And so your book says saying this is redundant. But all physicists say this, even though it's redundant. It's very hard not to say this. Okay, really we shouldn't be saying current flow, we should be saying charge flow. This is redundant because current is charge flow. Okay, but your book makes that point. So anyway, going back, whether we use conventional flow or electron flow, it doesn't matter. So let's try to get a better understanding of electric current. So let me draw a wire with the electrons moving through it. And by the way, what I'm going to say now not only works for electrons flowing through a wire, but maybe it can work for charge is moving through an electrolytic solution. Suppose I have a wire. And here's the cross-sectional area of the wire. And I want to know, I want to come up with a model of the electric current. I want to know what delta Q over delta T is. So imagine you have a bunch of charges over here, and they're drifting to the right with some velocity v sub d. I call it drift velocity. And these charges go from here to here in some time delta t, so that the particles travel a distance L v delta t. Okay? And of course, this is all full of charges. So these charges sweep out a volume that's equal to this distance times this area. So volume swept out is going to be V equals the area of my wire times L, which is the area times V sub d delta t. If I know the number of electrons per unit volume in this wire, or a better term is the number of charge carriers per unit volume, let's say N, then the number of charges that go from here to here in this time is going to be N times V. Okay, really this is the number of particles. The total charge then is going to be this quantity times whatever the value of the charge is. I can write this as Q, delta Q, however you want me to write it. Actually, I'm going to write it as Q, because it's actually the charge of each particle. So that's the total charge. Now, if I take the total charge and divide by my time interval, and so that's my equation for the electric current. That gives me a representation of electric current. Now this really represents an average value, because this drift velocity can really change. I mean, if you think about it, the electrons are going through the wire. They're plowing into the nuclei of the atom, and they're undergoing many collisions per second. Okay, they're going through many, many collisions per second. So this is really an average number. And we're assuming that the medium is pretty much uniform. So this is an average value, it's an approximation. And one thing that you see from this is the following. Take a look at this, and take a look at this. Let's say we have a positive charge moving to the right. If we have a negative charge moving to the left, I have to switch this sign and I have to switch this sign. If I switch both signs at the same time, the signs cancel. So a negative charge moving to the left is the same thing as the positive charge moving to the right. You can clearly see that there. So I can define one more thing, the charge per unit area. We call it the current density. So it's just I over A. Whoops. Sorry, that shouldn't have been a delta T, that should have been an N. I messed up. This is the current density. Again, this assumes it's constant. If the current density is not constant, then this is a more complicated expression. And again, I'm assuming that that's the case in this particular problem. Next week, I'm going to look at this from a more general point of view. Thing is, when we talk about electrons moving through a wire in practical applications, this is essentially constant. But there's going to be certain cases where it's not constant. And I want to bring it up because we're going to be doing problems involving magnetic fields. And you need to understand what this means for the case where J is not constant. Okay. Questions? Okay. So I went a little bit ahead of myself in the PowerPoint notes. I did email you the PowerPoint notes kind of late this morning. So again, your instantaneous current is your dq dt. And so delta Q is the integral of I dt. Of course, that assumes the I depends on time. So we talked about the fact earlier that 1 amp is a large value. The amp is a large unit of current. So let's do a quick calculation to figure out how many electrons per second is 1 amp. Well, that's 1 coulomb per second. Okay, so I'm going to take 1 coulomb per second and divide by 1.6 times 10 to the minus 19 coulombs per electron. The coulombs will cancel, the electron will come up here, and this will give me 6.3 times 10 to the minus 19, they're plus 18 electrons. So when you have 1 amp of current, you have that many electrons going through your wire. And because you have that many electrons going through your wire, you have all those electrons colliding and dumping their energy into the wire. So when you have a large current and it's dumping electrical energy into the material will warm up. That's why wires have limitations in terms of how much current they can carry. The more current, the thicker the wire has to be. Okay. So, what is the relationship between voltage and current? If you do an experiment, and you measure current through material as a function of the applied voltage, you will find that there are certain materials in which the graph is a straight line, meaning I is proportional to delta V. Not all materials have this behavior, but there are materials that have this behavior. Okay? And these materials obey Ohm's law. This is Ohm's law. And the ratio of delta V over I is equal to R, which represents the opposition to charge flow. Which means that I, the proportionality constant that relates these two, I is delta V over R. Now, for a material that obeys Ohm's law, two things have to be satisfied. First of all, this has to be true. And then R is independent of applied voltage. So both of these must be satisfied if the material obeys Ohm's law. If the material does not obey Ohm's law, this equation is still valid, but you're not going to get a straight line. You'll get something like this. And an example of this is a light bulb. And what happens in a light bulb is the light bulb gets hot and its electrical properties change as the material gets hotter. And so, although you can define a resistance for a light bulb, you're not going to get a straight line. Okay. Now, Ohm's law is kind of like Hooke's law. Because in Hooke's law doesn't always work, right? If you take a spring and you stretch it too much, what happens? You messed up the spring. It's not elastic anymore. Same thing with Ohm's law. If you take a material and you put too big a voltage across it, then it's going to start to heat up and R is going to change. Okay? Questions? Concerns? Okay. So, now let's talk about the units. Where do we go? Delta V over I is a volt per amp. The unit is the ohm, denoted by the Greek letter omega. Okay. Now, the ohm is actually kind of a small unit. So a lot of times we work in thousands or millions of ohms. So we define 1 kilo ohm as 10 to the 30 ohms, 1 mega ohm as 10 to the 6 ohms. And again, this is just an opposition to a charge flow. So let's talk about some circuit basics. What you're going to be doing over the next couple of weeks is you're going to learn how to characterize a circuit by measuring voltage, current, and resistance. But we also have to talk about a circuit. How do we characterize a circuit? So let me show you some parts of a circuit. Here's a drawing of a real simple circuit. You have a power supply, some device that opposes current, called a resistor, and some wires. So let me say a couple of things. Before I delve into this, let me say a couple of things. First of all, that picture you see is called a circuit diagram, a schematic diagram. And generally in this class, when I draw a schematic diagram, I'm assuming everything's ideal. So when I draw a wire, I'm assuming the wire is ideal. Okay. Now to denote a power supply or a battery, I use this. This is really a cell. And several cells can be drawn like this. Big line with little line. Positive, negative. Or if I have a power supply, I can put an arrow through it, meaning that I can vary the voltage. This is the schematic symbol for a power supply. Now the schematic symbol for a device that opposes current, called a resistor, is this. What is a resistor? Well, generally, a resistor is a device that opposes current. You can have these devices that obey Ohm's law, and you put it in your circuit, you call it a resistor. So I want to loosely define a resistor. A resistor that you place in your circuit is basically a device or element, circuit element, that is designed to obey Ohm's law in your circuit. Of course, if you put too much voltage across the resistor, it's not going to obey Ohm's law anymore. You'll burn it. Okay, but generally they're designed as a device to obey Ohm's law. Their job is to limit current. And when we do the Ohm's law lab, I'll show you an example of what a resistor looks like. They're little things. Okay, they could just be a wire. You can actually get a long wire and make a resistor out of it. The precise ones are basically long wires.
What are the red dots at the corners?
I'm sorry?
What are the red dots at the corners?
Oh, in that picture?
On the PowerPoint.
Yeah, I'm going to here. Let me click again. They're just points in my circuit. I'll get to them. They're just points in the circuit I'm going to denote.
Oh, okay.
Yeah. I mean, they're also, I mean, there's a name for them. They're called nodes. Where two or more wires joined together, we call them nodes. But in this particular case, I'm just using them as a mark of demarcation, I guess, if I can say it that way. So anyway, this is the symbol for the resistor. Okay. So let's take a look at this picture. And let me go back real quick. The green arrows represent the flow of electrons. The EMF means electromotive force. It's the battery rating. It's actually what it says on your battery, what the value is. The resistor, another term for the resistor is a load because it's actually sucking up the energy in your circuit. So we'll call that the load. It could be a light bulb. It doesn't have to be, I mean, I can replace that with a light bulb, which doesn't obey Ohm's law. But we can still talk about light bulbs in a circuit. In fact, your multimeter quiz involves light bulbs in a circuit anyway. The wires are, we're going to assume that the wires are ideal, meaning that their resistance is small compared to R. So we're going to ignore what happens to the wires, okay? Even though that's not really true. Real power supplies and real batteries have something called an internal resistance. So a lot of times when somebody draws a circuit diagram and they want to denote a more accurate version of the battery, they will draw an internal resistance with a little r. It doesn't mean there's a real resistor in your battery. That represents the effect the chemical properties has in the battery. It acts as if it's drawing some energy and not giving the full 3 volts to your load. And you draw the little R in there. Okay. For most of the problems we're going to do, we're going to ignore the internal resistance. In fact, in reality, you're supposed to have a power supply where that little R is as close to 0 as possible. If you're using a battery, that's not the case. When a battery gets older, that R gets bigger. And as that R gets bigger, the voltage across your load gets smaller until eventually, if that's a light bulb, the light bulb won't light up, and you recycle the battery. Okay, that's because your internal resistance is getting higher and higher. So really, what the battery is getting, what the load is getting, is something called a terminal voltage. That's the actual voltage across the device. And we'll talk about how to make the measurements next week. So the voltage across the device is called a terminal voltage. So I'm going to show you a simple circuit with a battery and a resistor, but actually I'm not going to use a resistor. I'm going to use a light bulb. Okay, so let me switch cameras. Or let me just switch real quick. Oops, I got it. Sorry. Maybe for some reason it's not working. There it is, finally. Okay, so this device came with your lab kit. This is part of your lab kit. It has batteries. These are the battery holders, and you have your 2 light bulbs. So I put this together. And so just to show you a simple circuit, I'm going to take the bottom battery, which has these 2 wires connected, and I'm going to hook it up to one of the light bulbs. So let me do that very quickly. So one of the issues you have to deal with here is that you're going to need a screwdriver. So your lab kit comes with the screwdriver. And so you're going to have to screw the wires on here. Now, these are very small, so it's hard for me to see. So I'm going to have a hard time screwing this in. And if you're going to turn the screwdriver clockwise, then you want to wrap the wire so that it wraps clockwise. Otherwise, it won't stay in place. So I'll put that in, and then on the other side, I'm just going to do it by hand. The other side goes to the other side of the bulb, and you see the light bulb goes on. And you have to have a complete circuit. The electrons have to have a closed path to go all the way around, because if not, the light bulb will go off. Okay? That's a simple circuit. And so if I were to measure the voltage across the bulb, it'll probably be different than the voltage from the battery because of the internal resistance in my circuit. Okay, let's take a look at a different circuit. Let me switch views. Here's another circuit, and I'm going to draw the ideal version of this on the board. Let me draw the ideal version of this on the board. without the internal resistance, because sometimes the internal resistance sometimes might confuse things. I'm going to draw my battery, my power supply. Okay, I'm and I'm not going to be careful. I'm going to call this a battery or a power supply. Okay, and I really shouldn't do that. Okay, so let's say this is 3 volts. This is the resistor. This is the resistor. Maybe I could call this R1 and this R2. Idealized version. So when I make this electrical connection, like this is a wire. This is basically a map that tells you how to wire the circuit. So I'm going to take a wire and go from here to here. Now the wire, again, we're assuming really has no effect on my circuit. So if this point's at 3 volts, this point is also at 3 volts. If this was not ideal, this would be a different value. This point, this is the same wire, is also at 3 volts. Same wire is also at 3 volts. Okay. And on this side, let's say I reference this side to ground to 0 volts. Then this, because I connect the wire from here to here, this will be at 0 volts. I connect this wire here, this will be at 0 volts. And then this wire here at 0 volts. So the potential difference between across the resistor, the voltage drops from 3 to 0. So R1 has a voltage drop of 3 volts. R2 has a voltage drop of 3 volts. And that's what's going to make the current go through it. You need a potential difference because the potential difference produces the electric field. And so electrons will go through here, electrons will go through here. But notice they're both at, the voltage drop is 3 volts across both of them. And so then we say the resistors are in parallel. Because the voltage across each one of them is the same. These 2 points are the same voltage. These 2 points are, let me rephrase that. These 2 points are the same potential. These 2 points are the same potential. As a result, the delta V across them is the same. And so we say they are in parallel. Because if I draw my internal resistance here, this will be a different value. That's why I drew the ideal case. Okay, because if I put my internal resistance in here, this will be a different number. The reason why I make this, I'm saying the resistance is 0, because Ohm's law says delta V is I times R. So even if I have current going through here, R is 0, so there's no drop here. There's no drop in voltage. Are we okay? So let me try to wire the 2 bulbs in my circuit in parallel. Let's try this. Okay, so I'm going to do the following. I'm going to connect, if I can keep that in place. So I'm going to connect this one to this one. Okay, and then I'm going to make life easy for myself. I'm going to take this wire, I'm going to hold it in my hand, and hook up one here and one here. And how come it's not lighting? Oh, I need this one too. Something's not working. Oh, I got the wrong one. Sorry. Okay. I gotta pay attention to what I'm doing. You guys all see the two are lit?
Yeah.
Okay. So those are in parallel. What I did was I didn't want to use a screwdriver because it would take me too long. I'm just holding these in place. Okay. So I connected this battery to this bulb, and then I have another wire to the top bulb. Just like the picture, right? Just like the schematic diagram. And then the other side of the battery, like so. Okay? So there I put the two bulbs in parallel. Now, let's look at a different case. Oh, I forgot to mention one thing. Wrong one. Actually, two more things. Any closed path in a circuit is called a loop. Any closed path in a circuit is called a loop. So there's one loop shown there. Do you see that there's 3 loops in that circuit? Let me go to the board. There's 3 loops here. 1, 2, 3. And any one of those loops can be used to analyze your circuit. And then this point here, are called nodes or junctions. Points where 2 or more wires come together are called nodes or junctions. Actually, I mean, really, the nodes are important when the current splits up into two different directions or more. Okay. So let's take a look at this circuit. In this particular circuit, I have 3 power supplies connected together, and then the red dots are just points where I'm points in a circuit I'm just marking. Okay, and I referenced the one side of the circuit to ground, so I know one point is at 0 volts in my circuit. Okay. All right, I'm going to go on the board and draw this circuit. So let me use my black marker. I have 3 batteries and really separated them for a particular reason. I'm going to draw a bulb instead of a resistor for fun. Okay, I grounded this point just so that this is at 0 volts, and that makes this point 0 volts. Because a battery maintains a potential difference between its terminals, if this is 0 volts, this point is at 1.5 volts. I took the positive of this side of the battery and took a wire and connected it to the negative of the second battery. And so this has to be at 1.5 volts. I'm referencing this point to this point. But because this is designed to maintain that 1.5 volts, then this point over here is going to be 1.5 volts higher. And then since this is at 3 volts and I connect this positive side to the negative side of this battery, then this point is going to be at 3 volts. And then this point will be at 4.5 volts. And since we're assuming ideal wires, then this is at 4.5 volts. This is at 0 volts. And so the voltage across the bulb is 4.5 volts. And so the purpose of the 3 batteries then is each time an electron goes to the 3 batteries, it gets a 1.5 volts times Q in terms of energy. Okay? So these are like 3 pumps, like 3 water pumps in a row. Every time the water goes through the water pump, it gains kinetic energy. And so, as it goes through these 3, it's got a total kinetic energy of 4.5 volts times whatever Q is. And so we say that these are connected in series. Because we can connect bulbs in series too, one after the other. What's the problem? What's one of the issues of connecting things in series? What happens if this battery dies?
The entire thing's done.
Yeah, it's as if I broke my circuit, right? The old days, the Christmas tree lights were connected in series. And so when one bulb died, you had to go through the entire series to figure out which one was dead. You'd have to take a spare bulb and take each one of them out and replace them with your spare bulb to find out when you find the bad bulb. Okay, which is painful. They've changed that since. Okay. So what I'm going to do is I'm going to hook up 2 batteries in series. You can do 2 bulbs in series too. I mean, it's one after the other. But I'm going to do 2 batteries in series so you get an idea of how to do this. So let me shift to the camera. Okay, so I hope you can see that okay. So I'm going to be using, so I have this bottom battery hooked up here. Let me disconnect this. Oops. So this is the negative side of the bottom battery, and this is the positive side of the bottom battery. I'm going to take the positive side of the bottom battery and connect it to the negative side of the top battery. Like so. I'm just going to twist them. And then I'm going to take the other battery, the positive side of the second battery, and connect it to the bottom bulb. Is it brighter now than it was before? Can you see that this one's way brighter than the other ones?
Yeah.
Because I've given them twice the amount of energy. So let me go back to the other figure. So what I did was I took the positive of the bottom one and connected to the negative of the top one, and then I connected the positive of the top battery and just connected it to one side of the bulb. Or the other side of the bulb, I'm sorry. That's what I did. So this gives you an idea of how to wire things in series or parallel. And you can do this with batteries or light bulbs. Okay. So what you need to learn how to do is to make measurements of delta V, R, and I. So your lab, which let me show you a picture of the document. The multimeter quiz is basically an exercise where you're going to videotape yourself going through 6 different exercises. so that you can demonstrate to me that you know how to use the meter, you know how to wire a circuit, at least the basic things, and then you have to learn, and then that you learn how to use a meter. I'm going to talk about how to use the multimeter next week. You got two that came in your kit. There's a larger one. In fact, let me switch cameras. Let's do this. You have a larger one, which will fit into the view, and then you have this smaller one. Hold on a second. The smaller one that you see there, and I would like for you to use a smaller one to make the measurements if you can. So each one comes with a manual. You should read the manual. Granted, they're not the greatest manual, but our document, our lab. I can send you a document for a different multimeter if you want. Granted, these are not the greatest manual for the multimeters. Okay, these are not expensive multimeters. So, but the multimeters are okay. They allow you to measure voltage, current, and resistance. In some cases, we'll be measuring capacitance. It is easy to measure voltage. It is easy to measure resistance, but it is a challenge to measure current. Okay? This one is hard to measure. Oops. What happened to the video? Something happened there. Okay. So, this was hard to measure. And if you make a mistake, you'll probably blow a fuse. The purpose of this exercise is to minimize the number of fuses you guys blow, because every time you blow a fuse, you got to contact us to get a new fuse. And they're not easy to get. You want to do this carefully. So next week I'll teach you how to do this carefully. Okay? But this is the one that causes problems. So, and I know I'm going along. I forgot two things to mention. Number one, there's a document on Canvas called a fatal current. Please read that. It tells you how much current you go through your body to kill you. 100 milliamps is lethal. So in your lab this semester, you don't have anything that's going to give you 100 milliamps through your body. So these are safe labs. We wouldn't have you do take-home labs with unsafe voltages. The voltages are going to be low. You're not going to get electrocuted. Okay. But anyway, 100 milliamps is lethal. When you get to around 10 milliamps, you start feeling it. Your muscles start contracting. If you really want to feel the effect of a shock, take a 9-volt battery and put your tongue on the terminals. You'll feel something. Okay? Kids do that when they're young. They kind of do things like that. Okay? So that'll give you an idea what the shock is. It's a small shock. But a bigger shock, as the current goes up, your muscles contract, and it makes it hard for you to let go of whatever your electrical device you're touching. When you get to 75 milliamps, it becomes lethal. 100 for sure is lethal. When you get to an amp, might not kill you, but it will start cooking you. And we're going to do a demo. I have Tyler who made a video showing you what happens when you get an amp or above through something. So we have a hot dog when we run the current through it of 1.5 amps. You'll see in about a minute it will be cooked. So it's due on March 7th. The multimeter quiz is due March 7th. Okay, so read through that. Additionally, there's a video called Series Parallel. series and parallel. If you search series and parallel, and then this guy called Electro, I like him because he's funny. And I didn't put that in a link in the module because it's not captioned. It's not well captioned. I think it's captioned in Chinese, but not in English. And I'm not allowed to use the auto, give you a link to something that has auto captions. So you might want to watch that video. Okay. In fact, this person has a lot of great videos. Some of them are captioned. Okay. So there's one. Just do a search in parallel and type electro room. You'll find his video. If you go on Canvas, and I apologize for going over. If you go on Canvas, in our modules, I want to point you to several things in our module on this unit, and then I'll stop talking. Let me go to modules. I have information on electrical safety, and I have 2 videos from that person. These are captioned, so you can watch the videos. So he's a pretty funny person, so he makes learning entertaining. But I also have a video to a simulation that you can use to help you learn how to make measurements with a circuit. So you can build our circuit very easily. And I'm going to show you how quickly I can do this. And it shows that the light bulb goes on. Then I can take a voltmeter and make measurements. And it'll tell you the voltage measurement, and I can measure current. So it'll tell you if you did something wrong. Okay. And so this is a great tool for you to actually play around with so you can learn how to build a circuit. You can actually throw in switches, resist. This is a symbol, this is our actual resistor. So I would take advantage of using this virtual lab so that you can learn how to make the measurements. That way you can do the multimeter quiz. And that one you have to film yourself demonstrating that you can do everything. Questions? Again, I'm sorry I went over 10 minutes. So next week I'll show you the multimeter and finish up the discussion.